Welcome to the online wastewater treatment operator certification training event. I'm Jason Flowers with Geosyntec Consultants, and I'm presenting this on behalf of the Arizona Department of Environmental Quality. This is Module 3, where we'll cover the basics of primary treatment, which typically includes primary clarifiers. So when we think about primary treatment, it's a sedimentation process is what we're talking about. So this is a physical process where gravity forces the separation of solids particles from water. Typically, the basic principle is something needs to be denser than water, hence it has a specific gravity greater than one, which means it'll settle out and then collect at the bottom of the tank where it will thicken as it collects at the bottom of the tank, which is an important thing to consider as we'll talk about later in the process. So let's talk about the functions of clarifiers and what they actually do. The first thing is flocculation. When the wastewater enters the cinder well, you'll get flocculation that occurs, in which you'll promote clumps and flocks forming at that point that will then cause for improved settling. By these larger particles forming together into bigger pieces, they will then settle a little bit faster. Then clarification happens, in which the solids and the liquids will then separate. The solids will then make up a good portion of TSS and BOD that is removed from that process once you have the solids separate from the liquids. Finally, thickening will happen as the sludge settles at the bottom of the clarifier. You'll have a compression that will happen as more and more sludge piles on top of it. You'll compress the sludge at the bottom, which will then dewater and cause the sludge to become slightly thicker. Lastly, you can use your clarifiers as short-term storage of solids in case you have some issue with your downstream solids handling process, but this is only short-term potential use of this because a high flow event could happen, and then all of a sudden you have solids washing out of your system further downstream and potentially overloading your other treatment processes. So when we think about primary clarification, what we are doing is we're, once again, settling these larger particles that want to settle out. The key thing to think about with this is that a good secondary clarifier can typically remove between 50 to 75% of TSS, and BOD removal between 25 to 40% removal. What is nice about this is that this suspended solids is typically faster settling than what you'd have in a activated sludge system. And so as a result, the size of these clarifiers can be smaller. And also the sludge will typically compact a little bit more than traditional activated sludge type system. So they're a nice, easy way to remove TSS and BOD from your system without having to expend a lot of energy. All right, let's talk about the basic function of primary clarifier. So as we mentioned before, influent or into the clarifier will enter the primary clarifier. The solids will settle down to the bottom and be removed as primary sludge will be sent over to solids handling process, whatever that may be. The clear effluent will then overflow and go to some biological reactor for secondary treatment. In addition, there's another part of this that you'll get some floating scum at the surface of the clarifier. You want to capture that material so it does not overflow with the clear wastewater, and you want to capture that scum and send that off for solids handling as well too. Let's look at different factors that affect clarifier performance. Number one, of course, is hydraulic loading on the clarifier. Each clarifier is designed for a maximum amount of volume that can treat per minute, per day, whatever it is. And so if you load too much into the clarifier, it can cause short circuiting, and it can also cause washout of solids that are present there. Number two, tank configuration. If you don't have proper baffling, and as a result of that, energy from the water coming in can cause solids to be scoured and released and leave the clarifier, that can impact it as well. Wastewater characteristics, and this thing can include particle characteristics as well. If you happen to have a wastewater stream that just does not have organics that don't settle well, they're not going to be removed in your clarifier, so you get poor performance related to that. Temperature, of course, as temperature decreases, the density of water increases, which then means that your particle needs to be denser to be able to be captured by it. Otherwise, it's going to float. And so that can have potential impact on your clarification performance. And lastly, if you happen to have industrial wastewater discharge that happens to have a lot of soluble BOD, well, that soluble BOD is not going to be removed by your primary clarifier. And so as a result, the clarifier, if you look at BOD removal performance, is not going to look great. So there's a couple of things that you want to think about in terms of what could impact your system performance. So when we think about different configurations, the two classic ones are circular and rectangular. There's a few others that are out there, but 99% of the clarifiers in the world are circular, rectangular. The choice of the configuration depends on site-specific considerations, including the space available, operator familiarity with the systems, maintenance requirements, and just the thought process in terms of the engineer. So either process works fine. It just, as long as they're operated well and within design parameters, they should perform their duty. But think about the circular clarifiers. There are multiple different types of feed systems for these, really just two, really. One is a center fed system in which the wastewater enters the center of the clarifier and then the flow divides between the two sides and will eventually overflow the weir where it leaves. So it's a center fed and goes out to the perimeter. There are peripheral fed systems which the wastewater enters on the side, and then you will get the circular flow that will then push the wastewater to the center and then back out again. I've seen less of those in the field, but I have seen those installed before as well too. Certain key geometry features associated with wastewater treatment plants. Number one, the sidewater depth. So typical sidewater depth of the clarifiers is typically 12 to 14 feet. The typical design. There's some that are a little bit shallower, some that are deeper, but 12 to 14 feet is a good range for the depth of your clarifier. It allows enough sidewater depth so you can build up a sludge blanket in your clarifier and not immediately get a washout of solids under a high flow type of situation. Next, an important feature is the center well. While it looks like just a place in which the wastewater enters, it does a few important things. Number one, it promotes flocculation, improve tank hydraulics. It can also help to reduce the energy of the water coming into the clarifier to minimize potential short circuiting in the clarifier as well too, by helping to take the energy out of the water and push it down rather than have it go directly out to the weirs and overflow. One of the ways that these center wells are designed to dissipate those energy are these energy dissipating devices that are built around the center well. So there's a million different flavors of them out there, each one of them with pros and cons. Their goal is, as I mentioned, just to decrease the velocity of the inflow coming into the system so you get better sedimentation. Ultimately, it's for you to judge which system you prefer best and to make sure it operates well in your system. As I mentioned, scum removal is also a very important factor to consider for your system because scum will form on the top of your surface. As wastewater flows through your system, lighter material will make it through and will sit at the surface of your wastewater. If you don't capture that and prevent that from leaving your wastewater treatment plant, it can potentially cause high TSS loads under various different situations. So the scum can be fats, oils, grease, debris. The scrapers at the top will typically have a scraper arm or like a skimmer arm at the top that will capture this material and push it into a beach where it is captured and carried away. In addition, you can have a scum baffle or should have a scum baffle that is right before your weir that is taller than your weir plate. And what that allows is that any scum floating on the surface would hit the scum baffle and will sit there and not go over the weir as well. Now, the way that your sludge removal mechanism works is important to make sure that you don't build up too large of a sludge blanket in your system. There are many different mechanisms that can remove it. The one shown here is a kind of a traditional scraper arm that spins around and pushes the sludge to a center well where it's then removed. But there are types that have a series of pipes along the length of the arm that sucks up the water at discrete points. And there's also long bars with perforated holes where a vacuum is also created too and just sucks it up through that long bar as well. Ultimately, just having a good mechanism to remove sludge so it does not sit around in your clarifier for too long is important for your system operation. This is just a quick picture of the more standard rotary scraper type system. You can see here, there's a series of the plates. As this thing spins around, it will slowly plow and push the sludge to the center of the clarifier, or where it is put into a hopper and then withdrawn through a pump that draws, that has a pipe at the bottom of that hopper. So for rectangular clarifiers, These systems, as they sound, are rectangular, and the flow goes from one side to the other side in terms of the operation. In addition to that, there are a chain and flight system that conveys the sludge from the bottom of the clarifier to wherever you want to collect it as part of that. And so it is an important part of the operation for this that the chain and flight system worked well. Another factor to think about is that for typically the depths of these are between 10 to 16 feet with some variation. Same story as the other ones. You don't want it too shallow because then if you have any sludge blanket in your clarifier and a big surge of wastewater comes in, it can disturb that sludge blanket and push that up and over and send it to the rest of your treatment plant, which may overload it. So just something to consider. In terms of the ways in which the scraper mechanism work, there are three different flavors here. One called concurrent, in which the scraper scrapes the sludge in the same direction that the water enters and leaves at. The countercurrent, in which the wastewater goes in one direction and the sludge is pushed to the opposite direction. And there are some folder flow designs where scraper will push the sludge in the middle of the clarifier while the flow goes from left to right in this scenario. So for rectangular clarifiers, we also need to evaluate the influent baffling. So there are three main ways that influent flow is baffled, although I'm sure there's others. Number one is inlet baffle walls. These are walls that are put right at the discharge point of the pipe. And what they do is they just break the energy of the wastewater entering the system, which then allows it to go settle down and slowly kind of help push the solid material down rather than just being jetted out into the clarifier and limiting your solids removal performance. Also, there can be T's as well, T inlets, in which will then have the wastewater be directed down through a T. This, once again, pushes the wastewater down to hopefully have solids settle out in that situation. Lastly, rear gate baffles can also be used. They are adjustable for very varied inlet flow and velocity requirements for your system as needed. So one important factor when thinking about primary clarifiers is detention time. It is effectively the amount of time that the wastewater needs to remain in the clarifier for proper operation. The way we measure that is the detention time. In this example, we're measuring in hours, is the volume of the tank in gallons divided by the flow of the wastewater in gallons per hour. We do that math, the volume divided by the flow in these units, you'll get the detention time in hours. So let's walk through an example problem where we're solving for what the detention time is. So you have a primary clarifier that has a volume of 100,000 gallons. If the flow of the tank is 88,000 gallons per hour, what is the detention time? Under this scenario, the detention time is equal to 100,000 gallons divided by 88,000 gallons per hour, which gives us 1.14 hours. That's how you calculate the detention time of a clarifier. Another important variable is a surface loading rate, or as I prefer to call it, the surface overflow rate. This is the amount of wastewater that flows across the surface area of a clarifier. The way I like to think of it as is it's a velocity. It is ultimately imagining the clarifier as a pipe, and this is the velocity of the water as it's coming up and over the weir, like it's a pipe that's being discharged. You don't want the value too high because then the upward velocity is too high, in which then any solid material will be then just carried up by it. But if it's slow enough, then the solid material can settle faster than that and be captured by the clarifier. So the way we measure this solids surface loading rate is the flow, and in this example, gallons per day, divided by the surface area, which is in square feet. So let's walk through an example. In this example, you have a circular clarifier with a diameter of 200 feet, and the flow to the clarifier is 2.8 million gallons per day. What is the surface loading rate in this example? Well, what do we know? Well, first we know that the diameter is 200 feet. We can use the area of a circle, which is pi divided by 4 times the diameter squared. In this case, pi divided by 4, pi is 3.14 typically. Take that divided by 4 and multiply that by 200 squared, which is 200 times 200. That number gives us 31,400 square feet. Now we have that number, which is our area, our surface area at the bottom, And then we need to divide that into our flow, which is 2.85 mgd. Now, in our equation here, we want this in gallons per day. Well, 2.85 million gallons per day is equal to 2,850,000 gallons per day. So we take to 2,850,000 gallons per day divided by the 31,400 square feet, and that gives us a surface loading rate of 90.76 gallons per day foot squared. Another important factor is the weir loading rate for clarifier. This is the amount of water leaving the clarifier per linear foot of weir. This design is used to determine the length of weir needed for a system because you don't want the loading rate too high in the weir because then you may have too high of a head loss associated with that. So operators can determine if the weirs are hydraulically overloaded by using the weir loading rate equation, which is the flow in gallons per day in this example divided by the weir length, which is in feet. So let's walk through an example of a weir loading rate calculation. You have a primary clarifier that has an influent flow of 1.7 million gallons per day. If the clarifier is 65 foot in diameter and has a depth of 9 feet, what is the weir loading rate in gallons per day per foot? So there's our equation, the weir loading rate, which is the flow in gallons per day divided by the length of weir in feet. Now you notice the depth is not in the equation, so we can actually ignore that detail there. We're just going to focus on the flow and the length of the weir. Now, how do we calculate the length of the weir? Well, the length of the weir is equivalent to the circumference of that clarifier in this circular clarifier design situation. So we take pi, which is 3.14 times the diameter, which is 65 feet, and that gives us 204 feet of circumference, which is our weir length in this situation. We now then take the weir load, take the flow, which is in 1,700,000 gallons per day, divided by the weir length of 204 feet. That gives us a weir loading rate of 8.33 gallons per day per foot. So a couple of standard design considerations for clarifiers. So typical detention time is in the range of 1.5 to 2.5 hours. The surface loading rate should be between 800 to 1,200 gallons per day per square foot. The weir loading rate should be between 10,000 to 4,000 gallons per foot per day. And when we think about the differences between the design of the circular versus rectangular clarifier, typical depths are between 10 to 16 feet for both. The diameter for a circular clarifier is between 10 to 200 feet. Rectangular clearly do not have a diameter. The lengths of a rectangular are typically between 50 to 300 feet, and the width is between 10 and 80 feet. But every design is unique and different as long as it's designed for your facility and for the wastewater you're being fed to the system, it should be sufficient. So one thing we're going to talk about operationally is your sludge removal considerations. As you mentioned before, the clarifiers can be used both for thickening as well as also for sludge storage. So that's something to consider is that they have that dual function in terms of number one, capturing the solids, but also doing some potential thickening associated with it. The thickening is correlated with the sludge blanket depth, which is related to this primary sludge withdrawal rate. You remove the sludge quicker, that sludge blanket depth will become smaller, and so you won't get as much thickening. So there's a balance between optimal sludge blanket depth to make certain that you thicken well enough, but also you don't make certain that that sludge blanket does not get too high, so you have potential washout to consider. So ultimately, kind of think about your plant to get optimal performance as well, because sometimes after your sludge was withdrawn, whatever is being handled, however the sludge is being handled in your wastewater treatment process after the primary clarifiers may have a particular design concentration it was assumed to be. And if you're too thin or too thick in terms of sludge concentration, that can impact the performance of whatever the primary sludge is being handled with, whether another thickener or being added to some kind of digestion system. One potential concern with primary clarifiers is short circuiting. Short circuiting is where you'll maybe have higher flow in one part of the tank. The result of that, you may have a situation in which solid removal is not as efficient. You can have solids carry over. A couple of things that can cause that. Number one, poor missing baffling can cause that, where you just short circuits and go straight. One thing I've seen frequently is uneven effluent weirs, in which a weir on one side is lower than the other. So then the water wants to go to that lower side, and the other side is less loaded. And so then you get much more hydraulic loading over one spot and causes a flush out that could happen there at that particular low spot in the weir. Lastly, plants growing in or trash getting in your weirs can also limit the performance and then prevent the water from going there. And the result, then other sections may get overloaded too. Other causes of short circuiting could be due to thermal stratification. Ideally, the wastewater is going to enter and flow evenly across the entire length of your clarifier from top to bottom. But there are certain circumstances that can cause that not to happen. Number one, depending upon if you've got too cold or too hot of water, the water could either run at the top or the bottom of the clarifier. And then effectively, there's space within your clarifier that is not active in dead space. And so you have a shorter retention time as a result of that. Also, wind can cause circulation cells within your system that prevent the water from mixing with that too. So these are all things to consider and to evaluate as part of your treatment system. So how can you monitor for short circuiting? First one is just do simple visual observation. Look at the flow over the weir. Look to see if there's a bunch of solids going over one particular part of the weir. That can tell you a sign that maybe something's happening. You can do a little bit more fancy of a test where you'll add in dye to the inlet and then see how the dye is spread throughout the area. Not as perfect, but maybe a nice way to kind of get a visual observation. Potential ways that you can solve for this is improve baffling for your system or improve EDI design as well that will break up the energy at the inlet and then cause for better flow throughout your clarifier. Let's walk through a couple of troubleshooting things that you can do for a clarifier in terms of performance. Floating sludge problem. So floating sludge typically happens when sludge sits in your clarifier for too long. So one way to solve that is to remove the sludge more frequently at a higher rate. Another thing could potentially happen is you need to repair or replace worn or damaged scrapers because maybe there's a spot where the sludge is not being removed and it's just sitting there, and the result that's causing the floating sludge. Also, repair or replace damaged inlet baffles too could be a potential solution. Septicity problems. To address this, you can move the sludge at more higher rates, similar type of situation where the sludge becomes septic because it sits around for too long and then methane builds up into there or nitrogen gas can happen. And so they'll cause it to float. Similar area, repair or replace worn, damaged sludge collectors. Should you add chemicals that add oxygen to the clarifier if you happen to have too long a retention time and you cannot change that? Or require pretreatment of strong industrial waste that are maybe causing this large amount of organic loading that's driving this. A couple other troubleshooting things to consider is if you happen to have sludge, it's hard to remove from the hopper. Consider improving the operation of your grit removal system because it could be due to grit getting into your primaries and causing it to cement in the hopper and causing poor sludge removal there. Also, you can increase the velocity of sludge withdrawal lines by either making the pipe smaller, which is a little bit harder to do, or increasing the pump withdrawal rate that can bring up the sludge velocity. Also, backflushing clogged pipelines, and then just more frequent sludge removal will also help too. If you're having some issues with TSS removal, one thing to consider is do you have the proper amount of tanks in operation? Maybe you need to potentially add additional tankage, or some chemical additions can be added to help improve temporary solid TSS removal by adding in some ballasting material to improve flock settling in your clarifiers. Also, frequently and consistently pumping your sludge is important too. That makes certain your sludge blanket is not too deep. Evaluate industrial dischargers. Maybe they're causing some hindering to settling due to the material in the waste. And lastly, eliminate potential storm flows like high I and I flow events, which can cause flushing events into your clarifiers, which can then cause poor TSS removal. To address erratic sludge collection removal operation, consider repairing or replacing damaged collection parts, remove debris from the sludge collector, of course, increase the frequency of pumping sludge from the tank. And then also annually draining and inspecting your tank is also very important. Now, if you have a broken chain, obviously, if the chain is rusty or corroded, replacing the chain, thinking of like a rectangular clarifier is also important. Make sure there's no misalignments with your chain system. and also make sure that no solids are interfering with the chain mechanism in the proper operation of that. With that, we finish our section on treatment process number 2, primary treatment on sedimentation. Thank you for joining us, and we hope you join us for the next module, which will be covering secondary treatment. Thank you.